Welcome to the EPG Patashala, the lecture series in computer science for the PG program, and this is the course compiler design, and we are in the 22nd module of the compiler design course, where we will be looking at the fourth phase of the compiler, which is generating intermediate representation. Objectives of this module are to understand the various types of three-address codes, to learn about the representation of three-address code, how do I represent the three-address code after computing it, and then to learn to write semantic rules for declaration statements to convert them into three-address code representation. So that is the last one will be, we will discuss about one type of three-address code generation for declarations today in this module, and then subsequent modules will discuss the other types of three-address code generations for other programming constructs. So quadruples, triples, indirect triples and types of three-address code are the keywords here. So consider this example which we have stopped at in the previous module. A three-address code is one where there is at most 3 operands. Okay, there is at most one operator at the right hand side of an instruction, and 3 addresses, basically only 3 addresses are possible. For example, here take the case b minus c, and here I am assigning it to t1. So t1, t2, t3, t4, all these basically refers to temporary variables. So b is a variable, c is a variable, b and c are looked upon at a particular address, and you compute b minus c and assign it to t1. Now as you can see, this is a abstract syntax tree which is abstract syntax tree representation, where I am actually looking at computing the internal node. The internal node are basically referred to with respect to your temporary variables. So here I am referring to this particular node as temporary variable t1, this as temporary variable which is t4, this temporary variable as t2, this is referred to as t3, and finally this is referred to as t5. So as you can see, t1 is nothing but b minus c, similarly t2 is nothing but a into this node, but this node is now got a name which is t1. Okay, so a into t1 is given to t2, and to compute this I can directly do it right away here, which is nothing but t3 is equal to a plus t2. Okay, and then t4 is nothing but t1 multiplied by d, and the last one is the root, which is t5, I am giving it a name, t3 plus t4. So this is the example of a 3-address code where you can have at most 3 operands and there can be only one operator on the RHS. Okay, so let us look at some types of 3-address codes. Okay, so you can have at most 3 addresses is what we said, at most 3 addresses. So x is equal to y operator z. So I can say y is an address, z is an address, left hand side x is also an address, and the operator can be any binary operator like addition, subtraction, multiplication or division or whatever it is. Or if I have only operator y, for example a is equal to plus plus b or a is equal to minus b. So where I have a unary operator here, unary minus, in that case my 3-address code will become x is equal to operator y. We already know there can be at most only one operator on the RHS, and that happens to be operator here. I can have 3 addresses at the most, therefore x and y are your 3 addresses are your addresses here, which is also called as a 2-address code here. So if it is a 3-address code, I can be fine with a 2-address code also. The third type of 3-address code is x is equal to y. This is simply an assignment statement where I have LHS is one address, RHS is one address. The RHS can have at the most one operator. That operator is missing here. So that is what we are trying to talk about here. The fourth one is called as unconditional jump, where I have a go to L. So go to a location labeled L. So L corresponds to an address. So I have only one address here in that case. Okay, so go to L is what we are trying to look at. The next one is conditional jump, where I have if x go to L and if false of x go to L1. So meaning that if x is going to be one address here, L is one more address, L1 is one more address. I have 3 addresses here, X, L and L1. Now X will be computed and the content of X I am looking at, okay. So I am looking at the same address here as well as here. So if it is true, I will go to a location L, else I will go to a location L1. And the next one is if X relop Y, go to L. So this conditional statement here itself can be computed using a relational operator, okay. So if X relop Y, meaning that again X and Y are 2 addresses and L is one more address. So I am computing that to branch to L. Again this can be combined with the previous one also, where I can say if X relop Y, go to L, and if false of X relop Y, go to L1. I can do that also. I can combine these two. And the next one is procedure calls or function calls. So where example parameter X, and I can have a call P comma N. So here X is going to be one particular variable, so one address. Here I have P comma N, again 2 addresses. So Y is equal to call P comma N, again here I have 3 addresses, okay. The next one is X is equal to Y of I and the reverse, I mean vice versa. If my index can be, if my array can be on the RHS, the array can be on the LHS also. So X of I is equal to Y. So what does it basically do? It computes Y of I, that is go to Y, look at index I, get its content and put it into X. So that is one the interpretation of this statement. What about this? Get the value of Y, go to X, move to index I and put it in that index location the value of Y. Again here there are 3 addresses, okay, X, Y and the offset I. Similarly I have here X comma Y and the offset I. The next one is X is equal to ampersand Y. This is a dereference scenario. X is equal to address of Y. So I am getting the address of Y and assigning it to X. So this is going to be X is equal to star Y, dereferencing operator. This is the address operator, this is the dereferencing operator. X is equal to star Y and star X is equal to Y. So here we are going to address Y. Again I have here 2 addresses only, X comma Y. Going to address Y, dereferencing it and assigning the value to X. Here I am dereferencing X, okay, and Y is given the value at address X, okay. So these are some examples. For example, if I have do I is equal to I plus 1 while A of I less than V, if this is going to be your example, the corresponding symbol, corresponding 3 address code will be like this. So where I will have to compute I plus 1 first, that is what I am doing here. I am also assigning a label here, do L, okay, and I say I is equal to I plus 1, so I will say I is equal to T1, which is computed in the previous line. Then I will say T2 is equal to I into 8, because I am assuming that the integer is going to be of length 8 bytes. I am going to do an A of T2, that is how much offset is necessary, assigning it to T3. So this is the value A of I am computing it in T3. I will check T3 less than V. If T3 is less than V, go to L. So this is a conditional jump. So I will go here. So this is a do while loop. So I will keep on looping till this condition is satisfied. Now all your programming constructs like while, do while, for, switch case, everything is going to be converted into this set of 3 address code statements only. Okay, I am not going to have a while, I am not going to have a for, I am not going to have a do while, okay, or I am not going to have a nested for, whatever it is. Everything will be converted to a sequence of if and a go to. It can be a conditional if go to, or it could be a simple unconditional go to also. So here this is what we have done. Now this is actually translated as a code with reference to position numbers, okay. Everything is assigned a line number. Again we will see all these computation, all these how do I get all these pieces of code by writing semantic rules for the same. That will be discussed as we move on in the subsequent modules. So here 100, I am just assigning line numbers as you could see, and then I am using that line number here for a go to branch. So this is an example from a textbook basically. So representing, okay, how do I represent this 3 address code? Now I have converted, okay, the previous slide looked at converting the information into a 3 address code. T1 is equal to I plus 1. Now where will I store this? Okay, to represent this, to put it formally, where will I put it is what we are trying to look at. So you have here three representations. One is called as quadruples, other one is called as triples, and the third one is called as indirect triples. These are data structures which are used for representing your three address code and putting it in a particular format. So your input, okay, which is a syntax tree, has now been converted to a three address code, and it is stored as a representation in the form of quadruples or triples or indirect triples. Out of all these three, indirect triples and triples are being followed compared to quadruples, because quadruples has one additional field in comparison with the other representations. So these are data structures which are nothing but tables, okay, and these tables are used to store your information, store your programming language which you have written it in so many lines of code, etc. It's been converted now to a intermediate representation in terms of a tabular representation. So the quadruples basically has four fields. The first one is an operator, second one is argument 1, argument 2, and then the result. Okay, consider this example. As I said earlier, this example is going to be carry forwarded for the sequence of examples. So A is equal to B into minus C plus B into minus C. Okay, I am not doing any optimization here. I am simply converting it piece by piece based upon the input syntax tree. Again, input is a syntax tree, output will be a three address code for that particular syntax tree. If you remember, the the type checking which is done in the third phase of the compiler, it outputs what is called as a syntax tree representation, and that syntax tree is fed as an input to a intermediate code representation, which is nothing but a three address code representer. The three address code has semantic rules for all programming constructs and then tries to use the syntax tree and then converts it into a tabular representation. So I have here A is equal to B star minus C plus B star minus C. So I can say T1 is equal to minus C here. Okay, looking at this first one, T2 is equal to B into T1. Okay, and then I see a minus C here. T3 is equal to minus C, and I have T4 is equal to B into T3, and then I say T5 is equal to T2 plus T4, and finally A is equal to T5. Now this we already know, because this is the basis for your derivation tree has been converted to a syntax tree representation, and that is what I have here. From the syntax tree, I am not getting this from this expression directly. I have a syntax tree as my input. From the syntax tree, I am getting this information. Now I will traverse the syntax tree, and I will know that every interior label is labeled with a temporary variable T1, T2, T3, T4, T5, etc. and it is operated upon the operator which is assigned in particular interior node based on its children values. Okay, so here T1 equal to minus C basically says that the interior node is labeled T1, whose operator is a unary minus, and its only child happens to be C. So this falls under the two address code category. So X is equal to operator Y. The next one is an interior node star, whose LHS happens to be B and RHS happens to be this node whose operator is a minus. But we know that now this node has been labeled as T1. Okay, so it's got B into T1 and so on. So this has been represented into a quadruple representation, which has got basically 4 fields, and this is the index field. Okay, 0, 1, 2, 3, 4, 5 is the index field referring to every row of the particular table. Now it has got 4 fields: operator, argument 1, argument 2 and result. If I have only one argument, argument 1 is filled, argument 2 is left empty, and the result, whatever you are computing, put it into the last component. So the first one is I have an operator as a unary minus, operand is C, and the result is stored in T1. So unary minus C and the result is stored in T1. The second one is B into T1, where B is an argument, T1 is one more argument, operator is a star. So star, B and T1, result is stored in T2. Okay. The third and the fourth are exactly like the first and the second, unary minus C and T3, star, B, T3 and T4. And the last one is T5 is equal to T2 plus T4. So plus is the operator, T2 is your argument 1, T4 is an argument 2, result is put in T5. And the last one is an assignment operator whose argument 1 is T5 and there is no argument 2 and result is put in A. Okay. Now as you can see that this particular column is redundant, okay, it is going to be reused. So therefore, or rather this column argument 2 is not going to be used completely for many scenarios. So therefore, these two columns, the argument 2 and the result column, can basically be combined into only one particular column, and that is the result of the next representation, which is nothing but the triple representation. So fields corresponding to temporary results are not used and references to the instructions are available. So the same example, argument 1 is the same for the first one, second one is B into minus C, right? So what is the argument 2? Argument 2 is from the row pointed by 0, okay. So this is again the row pointed by 2. Now the fourth one is we are going to operate on the result of 1 and 3. So the result of 1 and the result of 3 are operated upon is what is indicated here, and the last one is A is equal to the result of 4. So we have theoretically combined these two into a single one and then has represented either argument 2 in terms of the row indices only, okay. That is the triple representation. Argument 2 is replaced with the row indices, that is triples. Now there is one more thing called as indirect triples, okay. Just before we move on to indirect triples, one more example. How do I construct a triple for arrays? So we know that array has got two formats, x of I is equal to y, that is assigning a variable to an array operator, or computing an array operator's value and then putting it into a simple variable x. So the first one operator is this index operator, where I will compute x of y, that is I will use x's address and offset with respect to I, that is what this basically means. And then the next one is assignment operator, where I will use this is the target, okay, this is the target, so I am putting it here, and the second argument happens to be y, okay. So the target is specified in the case of argument 1, argument 2 will be the operator, the other operand basically. Now x is equal to y of I, that is your next situation. So what am I doing here? Again I am computing y of I here and then putting it into x, okay. So the result is x, so that is argument 1. Argument 2 is from computed by the 0th statement of the table, okay. So this is how you represent for arrays. I can use a similar thing for pointers also. So x is equal to star y, so how will that look like basically? So I have to use a star as the operator and there is only one argument y. So if it is only one argument y, I know that it is going to be resulting in dereferencing y, okay. Then I will have simply assignment operator, x will be the target here and this will be line number 0. So that could be the next representation. Indirect triples is, in addition to triples, we use a list of pointers to the triples. So this is again triples only, but we have double indexing, okay. So here 0 to 5 has got in pointers to the indices 10 to 15. So where 10 to 15 corresponds to doing this, okay, unary minus star, this we already have computed in the as a triple. So this is a triple, this has a pointer to a triple. So this is double pointer basically, so which is going to be one more representation of your 3-address code. Now we know how to put 3-address code into a representation or a data structure. Now our aim is to generate this 3-address code using semantic rules, okay. So that is a challenging task and that is very important for that is required for all your programming constructs. So whatever is our intention, that should be generated by the compiler, it should be done by the compiler, and that should result in correct computation and correct operation on the operands. So 3-address code is done based on the grammar construct. So the attributes which we are trying to refer to here are code, place, which is also referred to as address, and value. So every grammar symbol, actually typically here non-terminal, will have a code, it will have a address or a place and then a corresponding value, okay. So this is done by syntax directed translation, and based on this we will write semantic rules such that 3 address codes can be generated. Okay. So your grammar is there. Now this grammar has already got some semantic rules for handling type checking. Now it is going to have semantic rules for generating 3 address code corresponding to an intermediate representation for your particular programming language. So again, this is not dependent upon any target machine. It is simply converting your representation into a what is called as an intermediate code representation. Okay. So let us take this expression scenario and the semantic rules corresponding to the expression. So for let us take this first one. The first one is very simple. S produces ID colon equal to E. So as I already said, every non-terminal will have a code and an address. Address is nothing but the place, okay, or the memory where it resides. Okay. It can also have a value that we will talk about it later as we move on. So as of now, we'll talk about code as well as the address or the place which we are trying to refer to. Now, what will I do here? id.code, okay, id, okay, how do I, what happens actually here? Supposing if I say A is equal to B plus C, this S doesn't have any major role to play here. I will have to compute B plus C and put it into A. That is what we are trying to interpret this production. So what is my first job? My first job is to produce the code corresponding to E. Okay, my first job is to produce a code corresponding to E, and then that code is computed and it is assigned to this expression. Okay. So what will I do is S dot code, that is the LHS non-terminal will have a code, and that code is nothing but you first generate E dot code followed by this gen indicates generate. Generate top dot get id dot lexeme, that is this is id, so that you get it as it is, and that is equal to, when I put it in quotes, it means I'm trying to put it's a literally used value, that is equal to E dot address. So that E dot address is a place corresponding to E. So that can have a code, that has to first generate code, and that will have an address in which the code is basically available. So that will be used here, and I'll simply have a code as id is equal to E, or rather A is equal to some T1 or T2 or whatever it is. Okay. So this is the simplest of all statements. Then subsequently E produces E1 plus E2. So what should I do now? I have a code for E1, I will have a code for E2, and those will be available in a temporary location T1 and T2 respectively. For example, say I have to do addition of T1 and T2, and that is the code correspond to the LHS non-terminal. Okay, that is the code corresponding to the LHS non-terminal. So that's what we have here. E dot address is equal to new temp, that is the LHS variable now gets a new temporary location, and the code corresponding to this, okay, the code corresponding to this is nothing but generate code for E1 followed by generate code for E2. So E1 dot code followed by E2 dot code followed by gen. When I have a gen here, that is literally generated, that generates 3 address code here, which is nothing but E dot address, which you have created here as a new temporary variable. That variable is equal to the variable of E1 plus variable of E2. Okay. The next one is E produces minus E1. So again I have a temporary variable for E. Now I have to generate a code for E1 and then assign it literally with respect to the unary by introducing a new unary minus operator. So here E1 dot code is generated first, followed by gen. This gen alone generates your 3 address code statement. E dot address is equal to unary minus of E1 dot address. And the next one is E produces open parenthesis E1 close parenthesis, which is nothing but E dot address is equal to, now here there is no need for a new temp, because when I have a parenthesis here, I simply I'm trying to put it as a precedence. I'll evaluate this first. I'm setting up precedence alone here. Therefore, the code of E1 and the place of E1 could be copied onto E directly. Okay, so E dot address is equal to E1 dot address, and E dot code is equal to E1 dot code. And the last one here is E produces ID. So if I get an ID, that is to be taken as it is. Rather, the place of that particular variable should be considered as it is. So E dot address is equal to top dot get of ID dot lexi. Okay. The next will continue on this. So this is the same as I already said. So E produces E1 star E2. If I have a multiplication operator, what will I do again? LHS will be again a new temp. Generate code for E1, generate code for E2. Then generate the code corresponding to this particular production. How? Use a gen command. LHS will be a new temporary variable which is equal to E1 dot address multiplied by E2 dot address. So this equal to and star are literally used. So then this E produce ID just repeated so that you there will be some continuity here in the piece of 3 address code information. Now with that example, we will take this example here. Consider A is equal to B plus C into D. Okay. So this will start with the production ID colon equal to E, which derives E plus E, which derives E plus E star E, which derives ID plus ID star ID. So the corresponding syntax tree would be something like this. This is your corresponding syntax tree. This is fed as an input to the intermediate code generator, where I will look at this is nothing but my star. Okay, this will be encountered. I have to go from bottom to top, right? So this I mean, if I have to generate code for this, I should generate code for this. If I have to generate code for this, I need to generate code for this star node. So consider the star node that will have a new temp. That is your first semantic rule. Okay. So the semantic rule says generate new temp. So I am generating it as T1. And then I say generate code for E1, generate code for E2. So E1 dot code is simply C, E2 dot code is simply D. Then you do a gen, E dot code, which is T1, is equal to E1 dot code multiplied by E2 dot code, which is T1 is equal to C into D. So I do that and put it here. The next node is this plus node, where I will have again a new temp, which is similar to the star node only. So I am calling that as T2. I will generate code for B, which I have done. I will generate code for E2 also, which is now T1. Okay. So T2 is equal to B plus T1, that is your 3 address code. And finally the root will be, this is a new temp. Okay. T3 is equal to T2, and finally we said S dot code is equal to E dot code, right? So we will say A is equal to T3. So this is the example. This example basically discusses the 3 address code corresponding to expressions. Okay. There will be more expressions. We will move on to it as and when we encounter. We will be talking about assignment statements with respect to arrays, etc. So we will see that as we move on. The next one is declarations for 3 address code for declarations. Now the types are type, width and offset. So here you have a offset and a width. So this is the Pascal syntax. So when I see a declaration, I will just set offset is equal to 0 to start with. And then as I encounter a declaration, ID semicolon T, T is the type of your data type that is given to ID. Okay. So I will say this is enter here is creating a new symbol table. When a declaration is encountered, you create a symbol table and put it into that basically. So what do you put into that? You will put this variable name, its type and offset. So to start with, offset will be 0. After that, I have seen one variable now, therefore I have to increment offset by T dot width. Okay, that is what it has done here. The next one is T produces integer and T produces real. Integer type is integer, width is 4, real type is real and width is 8. Okay. And the last one is array of num of T1. So what will I do here? T dot type is nothing but an array who has, it's a 10 element array or a 20 element array, etc. of type T1. The last one is T dot width is equal to num into T1 dot width. Okay, T dot width is equal to num into T1 dot width, because you have so many elements that is multiplied with T1's type and then you are incrementing the width. And in that case, T produces arrow T1, this is a pointer. In that case, this is a corresponding semantic rule. Now, these will be put into the symbol table, and every time we encounter a declaration, a new symbol table is created, and when you encounter a procedure which is nothing but a function, one more symbol table is encountered. Now our job will be to interconnect and maintain the symbol tables that is available and who can access which symbol table. Okay, that will be discussed in the next module, where we will talk about symbol table management and for declarations to incorporate scope of your variables. So on summarizing this module discussed the need and ways of intermediate representation in terms of quadruples, triples and indirect triples were discussed, and we also talked about the three-address code for declarations in the simple context. So we'll continue on this in the next module. Thank you.